Good evening. My name is Janet Miller, and I'm a member of Concord's Comprehensive Sustainability and Energy Committee, CSEC. I'm here to welcome you all to the kickoff event for our Cooler Concord Sustainability Series. We're very grateful to Dr. Kerry Emanuel for participating in this series tonight by giving a keynote address, Climate Change, Risks and Opportunities. This evening's talk will be followed by 5 other events in the coming weeks, all of which address actions we can take to help the environment and lower our carbon footprint. CSEC is collaborating with several other environmental groups in Concord to put these on, including the Sunrise Movement at the Concord Carlisle High School, which is helping us with this evening's event. You can learn more about the upcoming events at our Cooler Concord website, coolerconcord.org, and there are flyers with information about these events on Concord sustainability on the table outside the hall this evening. Dr. Emanuel will be available to answer a few questions at the end of his talk. If you're in the audience here, you may come up to the microphone, or if you're on Zoom, you can raise your Zoom hand to ask a question. This event is being recorded and will be available on the Minuteman Media Network. With that, I would like to introduce Delphine Garot, a representative of the Sunrise Movement at the high school, who will introduce Dr. Kerry Emanuel.
Hello, everyone, and thank you all for being here tonight. My name is Delphine Garot, class of 2022 at Concord Carlisle High School. I am a co-leader and founder of the CCHS Hub of the Sunrise Movement, and I will be moderating tonight along with Janet Miller. Sunrise is a national youth-led movement dedicated to promoting governmental climate change action. Sunrise has organized global climate strikes, political sit-ins, and worked hand in hand with politicians to push for progressive climate policies like the Green New Deal. The CCHS branch of Sunrise now has a committed group of about 15 members. We have so far promoted the movement's agenda by chalking sidewalks to display our message, hosting fundraising events to raise money for our future actions, such as the shirts we are wearing tonight, participating in a lobby day through Our Climate to get our state legislators to focus on climate legislation, and most recently, marching in the Patriots' Day Parade. Our hope is for Concord Sunrise to become a long-standing platform where students can voice their opinions on climate change to the community and advocate for widespread system-level reform to stop it. I'm here tonight to introduce our keynote speaker, Dr. Kerry Emanuel. Dr. Emanuel has been a professor of meteorology and climate science at the Massachusetts Institute of Technology since 1981, after spending 3 years on the faculty of UCLA. He specializes in hurricane activity physics and was the first to investigate how long-term climate change might affect hurricane activity. Dr. Emanuel is the author or co-author of over 200 peer-reviewed scientific papers and 3 books, including Divined Wind, The History and Science of Hurricanes, published by Oxford University Press, and What We Know About Climate Change, published by the MIT Press. He is also co-director of MIT's Lorenz Center, a climate think tank devoted to basic curiosity-driven climate research. We are very fortunate to have him with us tonight. Please join me in welcoming Dr. Kerry Emanuel.
Thank you so much for that very generous introduction. I'm really happy to be with you this evening. Although, of course, I wish I could be with you actually and physically, and I hope that time will come soon when we can do that. But I'm speaking to you from the coast of Maine tonight. And I'm going to share my screen here. And I want to talk to you about several interesting aspects of climate change. Not only the science behind it, which is what I will lead with, but what really are the risks. And this is very important, the opportunities I like to stress that there's an upside to this. It's not all gloom and doom. And I'm going to argue that the transition away from fossil fuels will have a lot of benefits for us, even apart from what it would do to curb climate change. So the program for this evening is to begin with a very brief history of climate and climate science, just to give you a little background of where scientists like myself are coming from, to talk about the real risks of climate change and try to put some numbers on them, and then talk about the very interesting and relatively young field of quantitatively estimating climate risks. You may be surprised at how little progress we've made in this field, but we're beginning to pick this one up. And then I'm going to talk about solving the problem. And rather than to paint this as a huge sacrifice we all are going to make, although to be sure there will be sacrifice, I'm going to also paint it as a golden opportunity to go to a better kind of living. Okay, so let's begin with just a quick recap of some of the many of the Earth's quite interesting and wonderful climate variations. I'd like to preface my remarks by saying that we who do climate science got into it for the same reasons that almost all scientists go into science, because we're utterly fascinated by the subject. It's not because we necessarily want to save the world. It would be nice if I could claim that that was my main motive, but to be honest, it wasn't, at least in the beginning. Even if we did not have global warming, it would be a very vibrant field because it's a really fascinating subject. And I want to say particularly to the students in the audience that this makes it a really nice field to go into if you find it half as fascinating as I do. And even if we aren't necessarily always concentrating on the problem of global warming. So let me give you an example of the sorts of things that happen in climate science. And one of the most successful subdisciplines has been the discipline of paleoclimate, which looks for signals or proxies for climate change in the geological record. And I'm showing you three such proxies here. So this is a series of graphs that go back 450,000 years on the left side to the present on the right side of the graph. And these are the top two curves are proxies for temperature. The blue curve is for a site in Greenland, and the green curve is for a site in Antarctica. And you can see the labels on the axis here in temperature departures from some kind of mean in degrees centigrade. Well, the first thing you see, if you just look at the squiggles of the blue and green curves, is they're very nicely aligned. The changes that are being recorded in Greenland and Antarctica are pretty much in sync. And so we really are measuring something like a global change. And what you see is that the last 450,000 years has been generally cold, but with some upward spikes. Here's one at about 330,000 years, another about 240,000 years, another about 120,000 years, and another one today. These are called interglacials, and the cold periods are called glacial times. And you can see that they're pretty much coincide in the two hemispheres. This is a worldwide phenomenon. Now, the bottom curve isn't temperature, it's ice volume. It's the total volume of ice grounded on land. It doesn't include sea ice. But low is plotted on the top and high on the bottom, so you can more easily visually compare it to the other curves. And you can see that that's very well aligned too. Now, the remarkable thing about this is you might be asking, how the heck can you know about the volume of ice on the planet 400,000 years ago? And that's itself a remarkable story. I don't have time to tell you, but it has to do, or the actual proxy is the ratio of two isotopes of oxygen in the shells of microorganisms buried in deep sea sediments. Remarkably, they are a measure of ice volume on the planet. It's a wonderful field. Now, if we go back 20,000 years or so, in the peak of the last glacial episode, here is a rendition or a depiction of what the land ice in North America would have looked like. There were two ice sheets, the vaster being the Laurentide, and where you are, if you're in Concord, assuming you're in Concord, you were under about a mile of ice back then. That's a lot of climate change. Up here in Maine, maybe even a little bit more, okay? That's a dramatic change in climate from what we have today. Now, if we look at what happened as that last ice age was ending, one of the consequences is that when land ice melts, the water goes into the sea and sea level rises. So this is a record of sea level from proxy data. That's another long and interesting story, going back to the peak of the last ice age, the last glacial maximum about 24,000 years ago. And you can see back then, sea level was about 130 meters lower than today. It's about 400 feet. That's a lot of sea level change. If you could have crawled out from under the Laurentide ice sheet, you could have walked to Provincetown without getting your feet wet. There was no water in the bay. So if you look at this curve, sea level came up over a period of about 15,000 years, and it stabilized about 7,000 years ago, which maybe by coincidence, but probably not, is generally reckoned by anthropologists and others to be the beginnings of human civilization. We've been around for a long time as a species. This is when we really started to settle down and farm and herd livestock and so forth. So civilization developed at a time of remarkably stable climate, as here represented by sea level, and today is extremely fine-tuned to this climate. So this is an incredibly important point, because if we take this stable climate and we perturb it, whether it's up or down, it's going to be disruptive for no better reason that we're extremely finely tuned to the climate we've had since the birth of civilization. Now, a remarkable achievement of climate science is we pretty much know why these ice ages happened and will continue to happen. And it has to do with very predictable variations in the orbit of the Earth around the sun and the Earth's rotation on its own axis. And various scientists worked on this over the years, most prominently the Serbian mathematician Milankovitch, whose portrait you see here on the left. And there are three principal kinds of wobbles. The Earth's orbit, as many of you know, is elliptical. It's not circular. So sometimes of the year we're slightly closer to the sun, others we're further away. But the degree of that ellipticity varies on about 100,000 year time scale. Okay. The Earth's axis tilts with respect to the plane in which the Earth orbits the sun, and the degree of that tilt wobbles on a time scale of about 41,000 years. And finally, the Earth's axis precesses, much like a top that's tilted on a table, and that has two periods of around 19 and 23,000 years. Now, how come we know that this is responsible for the ice ages? Well, here's another interesting chart. This goes again from time going forward from left to right. This goes back 1 million years. So the numbers on this bottom axis are in thousands of years. So 1,000, thousands, 1 million years up to the present. And this is based, there are two curves on here. The red curve is pure math and physics. It's Milankovich's orbital math, if you will. This time converted to the total amount of radiation entering the high latitude northern hemisphere. And so it's summertime insolation. There's no sun in the winter at high latitudes. The other curve, which is completely independently measured, is the ratio of two isotopes of oxygen in the shells of ancient marine organisms that have settled to the bottom of the sea. All right. And are a measure, as I mentioned to you before, of ice volume. It's actually not the ice volume itself, but its time rate of change that's plotted here. And you can see how beautifully these curves are aligned for the most part. So this is a confirmation of Milankovich's hypothesis that the Earth's, this kind of glaciation is governed by how much sun is coming into the high latitude northern hemisphere in northern hemisphere summer. Okay, so we do know something in climate science. Now, this brings me to another interesting story, which is the discovery of and quantification of the greenhouse effect, which you've all heard about, of course. And it really dates back to the really good quantitative measurements date back to this Irish physicist, this dour-looking Irish physicist, John Tyndall, who was a bit of a polymath. And among many things he did, he was the first to quantitatively measure the greenhouse effect. He built this apparatus, which if you want to see the real thing, it's on display at the British Museum. And it consists of a long tube, and he could fill that tube with a gas of his desire, oxygen, carbon dioxide. And then he'd shine a bright light through the tube of many different wavelengths of light and measure how much of the radiation that was emitted at this end made it down through the end of the tube. So he could measure how much radiation of different wavelengths was absorbed by whatever gas is in the tube. So the first thing he tried was oxygen and nitrogen, which, as you probably know, together make up about 98% of our atmosphere, and couldn't find anything at all. And I was very discouraged at first. But then he kept going, and he discovered that some of the trace gases, particularly water vapor and carbon dioxide, absorbed almost everything going down that tube. And so what we now know, thanks to his measurements and later understood by quantum physics, is that the bulk of the composition of the atmosphere, nitrogen and oxygen, don't do anything. Radiation of all wavelengths, sunlight, infrared radiation go right through. Argon is the next most plentiful. It didn't do anything either. The greenhouse gases are that orange slice. Now, I don't know about your eyesight. I can just barely see that on my screen. Together, they make up 0.25% of the mass of our atmosphere. But that orange slice definitively makes the difference between the mean surface temperature of around 60 degrees Fahrenheit we enjoy and 0, well below freezing. So this is very important. And it was a shock to the scientists of that day, but it's been accepted for well over 100 years that this is the case. And you might think, well, that's not very intuitive, but if you're in a big room, the temperature is being controlled by a thermostat, which in the old days had a tiny little bead of mercury in it. And that mercury, even though it was tiny, tiny fraction of the mass of the room, controlled its temperature in some sense. It was a part of a thermostat. This orange slice is part of an Earth thermostat on a long time scale. Now, what is the greenhouse effect? It's not that hard to understand, although it doesn't have much to do with greenhouses, it turns out. So let's consider first a cartoon of an atmosphere that didn't happen to have any greenhouse gases in it. Let's just take the Earth situation, but take all the greenhouse gases away. It'd be a very simple calculation for physicists. And what's happening is sunlight is coming in, being absorbed not by the atmosphere at all, but by the surface. And the surface would continue to heat up. And the only thing that balances it is the fact that the surface emits infrared radiation. You can't see it. It's much longer wavelength to space. And that's a function of temperature. So it's very easy to calculate how warm the surface of the Earth would have to be to radiate enough infrared radiation to balance the absorbed sunlight. And that temperature is 255 kelvins, about minus 18 degrees centigrade, sort of close to 0 Fahrenheit. It'd be really, really cold if we didn't have greenhouse gases, but we do. And what greenhouse gases do is they both absorb the infrared radiation coming up. By the way, they have very little effect, not quite 0, but very little effect on sunlight. Sunlight just pretty much comes right through them. But they absorb infrared radiation coming up from the surface, and then so that the atmosphere doesn't keep getting hotter and hotter and hotter. It also emits infrared radiation, and it emits it up and down. Now, if you're at the surface, what that means is you're getting energy not just from the sun, but from the atmosphere in the form of infrared. And that radiation coming from the atmosphere, and I should say the clouds within it as well, is going 24/7, right? It's just as strong at night as in the daytime. And in fact, on average, the surface of the Earth gets twice as much radiation from the atmosphere as it does directly from the sun. And so it has to warm up to balance both the sunlight and the back radiation from the atmosphere and the clouds. That's all there is to it, okay? The Earth's surface has to get warm enough to balance not just sunlight, but back radiation from the atmosphere. Now, this fellow, Svante Arrhenius, who lived toward the end of the 19th and early 20th century, was a Swedish chemist. He looks even unhappier than John Tyndall. You know, I got to thinking, have I ever really met a jolly climate scientist? Have you? I don't know what it is about the field. But he dabbled, like many physicists and chemists of the era did, in other things. And he was the first to start to wonder whether burning lots of fossil fuels might actually change the CO2 content of the atmosphere. And he predicted that if you were to double the CO2 content, you'd raise the Earth's surface temperature by about 4 degrees centigrade. And if you increased it by by fourfold, the temperature would go up 8 degrees. So he understood that it was a logarithmic increase. And if you compare his numbers to the modern estimates of between 1.5 and 4.5 degrees C, considering he had no computers, pretty poor measurements, it was a pretty jolly good estimate for an early one. And was he right? Well, I'll let you decide. Here is a graph of the carbon dioxide concentration going back to the end of the 19th century up pretty much to the present, not quite the present. And it's not the CO2 itself I've graphed here, it's its natural logarithm, if you know what that means. If you don't, it's just another measure of the concentration of CO2. And on top of that, I have superimposed a record of the Earth's mean surface temperature, which is pretty reliable back to about 1880 or so. Now you can see that there are a lot of ups and downs and jiggles, but by and large, this curve follows the logarithm of the carbon dioxide that just as Svante Arrhenius predicted. And one of the things you should realize is that our understanding of climate and of global warming in particular is not based, as some would have you believe, on hopelessly complicated black box models that were developed over the last few decades. This, folks, is just basic physics going back well over 100 years in time. And so the fancy computer models do add value. They tell you something about how the distribution of temperature change both across the Earth and vertically. The basic physics has been known for a long time. Now, just to show you how hard we're pushing the system, we also get, from looking at ice cores and looking at bubbles of ancient air that were trapped in the ice cores, we have a good record of carbon dioxide content of the atmosphere going back about 800,000 years. So this graph goes from 800,000 years ago on the left to today. CO2 content does vary naturally with the ice ages for reasons we're beginning to understand pretty well. But this is where it is a few years ago. I have to keep updating this graph every time I give this talk. Actually, this is where we are today, a little bit above, about 420 parts per million. That spike is what we did. And there is absolutely no doubt whatsoever that we did it. It's not just that it's a spike, it's the particular isotopic composition of carbon dioxide that is a fingerprint of fossil fuel combustion. So that's what we're doing. We're taking the most important long-lived greenhouse gas and we're really twirling it. We're really torquing it. It's like taking a thermostat and just giving it a good spin in one direction. Now, the problem is that as much as we know about science, one of the great advances in any science, but particularly predictive science, is not only being able to make an estimate, but being able to quantify the uncertainty in that estimate. And there's no climate scientists in this prediction business who would ever claim we're very certain about what's going to happen. What I'm showing you here is an estimate based on many, many, many computer simulations in this case of the Earth's response to doubling carbon dioxide when the climate has, if you just instantaneously doubled it and then let the climate settle down. This is the global change in temperature. And you can see that the most probable, the number of simulations that gave you the most, were in the sort of 2 to 3 degree range. All right. Now, if you, as I'm going to do shortly, try to translate this into what it means for us, there's not much risk if it turns out to be this 5% tail down here, where it's well less than 2 degrees. Things will happen. We'll have to adjust. Not likely to be catastrophic. In the middle of this range, it's pretty risky. We're not quite sure how risky it is, but if nothing catastrophic happens, nevertheless, it would be pretty dangerous for civilization. Out here, we're in the tails, more than 4.5 degrees. Undeniably, it would be catastrophic for civilization, not for the Earth, but for us. Unfortunately, that's for doubling. And we are, by the end of the century, if we don't do anything, going to go well past doubling carbon dioxide. So this is a graph of CO2 content up to the present, which is around here. You can see it slowly increasing. And then these are projections going forward that all depend upon assumptions about how human beings behave. All right. So the purple curve is if we just keep on going, business as usual. And the other curves are various measures taken to curb CO2. The blue dashed line is doubling the pre-industrial value. So we sail past this doubling in the mid-century if we don't do anything. In fact, if we don't do anything at all, we're going to more than triple CO2 content by the end of the century. Now, what does that mean for the Earth, and what does that mean for our actions? So one thing that you have to understand about this is once you put CO2 in the atmosphere, it stays there for a very long time. Okay, it doesn't, if we stop emitting, it's not like we wait a few weeks and everything's back to normal. That's not true at all. These are estimates based on calculations of carbon dioxide content. Actually, it's also history of CO2 content, parts per million. And then we assume that when we get to 450, 550, 650, or 750 or higher, we're suddenly going to turn off the emissions. Obviously, that can't happen, but let's just assume that. Don't mind my ship's clock. I haven't figured out how to turn it off. And what you can see is that once you turn off the emissions, there's an initially rapid decline. By rapid, I mean over 100 years or so. But then it really tails off. If we go all the way to 1,200 parts per million, okay, it tails off and maybe goes down to 750 by the year 3000. It takes a long time. And that's why whatever decisions we make when we're on this upside of the curve, which is where we are now, have a very, very long span of influence, unless we can figure out how to suck the CO2 back out of the atmosphere artificially. Now, the temperature that goes along with that is on the bottom graph. And owing to very interesting compensations to a good approximation, the temperature you have when you turn off the emissions is the temperature you're stuck with for 5,000 or 6,000 years. All right. So this is not something that goes away fast. That's why, since we're on the steep upward part of this curve, we're kind of a special generation or two, and the decision falls to us, and whatever decisions we make have implications out for many thousands of years. All right. Now I want to talk a little bit more tangibly about what this all means for us, which are climate risks. And I want to make a very, very clear point to you, which probably is fairly obvious. I would argue nobody really cares whether the world will warm up by a few degrees. I don't care. All right. If that's all it is everywhere the mean temperature is a little higher and we don't alter any other feature of the climate, well, it's like moving from Boston to New York or something. Okay. That's not really what we care about. What we care about are the real risks that go along with this warming. Heat waves, wildfires. There's huge wildfires going on right now in the US Southwest. Hurricanes, droughts, floods, and so forth. That's what we really worry about. Those are the things that hurt us, okay? heat waves could be considered to be part of this warming, but again, it's the big spectacular increases over a period of a week or so that kill us. So one thing we are trying to do now to be able to really understand these risks is to price them or quantify them, including all importantly, our uncertainty about that, so that we can make intelligent choices. Without knowing what these risks are, we don't know how much to spend, if you will, to counter those risks. One instrument for pricing risk, but only one, is insurance. But for various reasons having to do with regulation and politics and so forth, it's not even today accounting for the climate change that's already occurred. The insurance business is pricing your homeowner's risk, for example, based on historical records going back 60 or 70 years. And it's not actually accounting for the climate change that's already happened, let alone climate change that will happen. But the good news is, I would argue, science is positioned to make rapid progress in quantifying climate risks. Now, the reason, the important thing about this is that long-term risk, not just climate, by the way, almost all risk, is dominated by extreme events. What do we mean by that? Well, it's an anthropological statement, and that is that societies are usually very well adapted to frequent events, where frequent is sort of roughly greater than once per 100 years. Now, what's magic about 100 years? I don't know. A few human generations. If something bad happened to you, you remember it. If something bad happened to your parents, you either remember it directly or they'll tell you. Ditto your grandparents. Go back to great-grandparents, yeah, maybe not, okay? Conversely, societies are often poorly adapted to rare events. It's not worth it to build a house strong enough to take a once in 500-year windstorm, for example. Your house isn't going to last anything like that long anyway. So the problem is that if you can get very large increases in cost when something that was infrequent becomes frequent. Because infrequent events are damaging. If they become frequent, it takes a while for human civilization to adapt to that. That's where the trouble happens. So here's a kind of a curve. What I've done is take any hazard. It doesn't actually matter what it is. It can be an earthquake, tornadoes, hurricanes. And on this axis is the percent of property destroyed by that hazard as a function, not of its intensity, but of something called the return period of that. So the return period is sort of the inverse frequency. A return period of 100 years means it's a 1 in a 100-year event. So these are common events. These are uncommon events, all right? And the steep part of this curve for almost all phenomena that we make a graph like this for is about 100 years, which is really interesting. So the largest slope is around 100 years. And that means something that was a 150-year event becomes a 50-year event. You're moving this curve over here. Suddenly, really damaging events become frequent. And then we've got a problem. So the problem is that all the risk assessments are based on just too few years of data, but they don't assume that there's any shift in this curve at all. So all current risk assessments are based on historical statistics, all that are used by industry, governments, and so forth. These historical records are often much too short. To get a 100-year event, you need 1,000 years of data. We don't have that. Moreover, the last 50 to 150 years of statistics we do have turns out to be a poor guide to the present because of climate change that's already happened, all right? So global warming isn't about the future only, it's about now, all right? Because we're estimating risk based upon outdated hazard records. The people in the risk modeling industry have been very slow to migrate away from an historical basis for risk assessment and to using physics to estimate risk, which is what I'm going to talk about next. And I'm going to give you an example from my own field, which is hurricanes, estimating hurricane risk. So hurricanes are amongst the most damaging hazards. Globally, about 10,000 deaths per year since 1971. $700 billion in damages since 1971. And this is the scary part. The global population exposed to hurricane hazards has tripled since 1970. Now, the whole population hasn't tripled since then. People everywhere are migrating into hurricane zones. And this is a big problem. Is hurricane risk changing? Well, here's a graph showing the global amount of damage done by hurricanes as a fraction of world domestic product. That's sort of a normalized measure. These are the numbers here. You have to multiply them by 10 to the minus fourth. And you can see that they're going up pretty rapidly. There's been a 380% increase since 1970, but most of that is simply because the population has increased so rapidly. And of course, when the population increases rapidly, they throw up buildings and houses and infrastructure, and there's much more to damage. And that population increase is about 200%. So that suggests there's still something left over. It suggests, but by no means proves that climate change has contributed to increasing damage. Now, the records of hurricanes themselves are very poor outside the Atlantic, which is only about 10% of the world for hurricanes. And this blue curve shows the annual number of major hurricanes, category 3, 4, and 5, going back to about 1900. That's the blue curve. You could see it going up. This red curve is a calculation based on a hurricane synthesis program that we developed at MIT. And it sort of follows along pretty much the historical record. So there's an indication of a fairly rapid century-long increase, although there was this very interesting dip in the 70s and 80s, which we now understand pretty well is also a man-made effect. It was due to, this is pre-Clean Air Act, combustion of coal, oil, and gas puts particles in the atmosphere that reflect sunlight and cooled the North Atlantic over this period. Now, on the other hand, if we look at the globe, this is just the global number of tropical cyclones everywhere in the globe. We can only go back to about 1980, ups and downs, but no real trend in that number. On the other hand, this is a graph showing the fraction of storms. This is only from 1980 to the present. Again, the fraction of the storms that are of major hurricane category. And that fraction has been going up. So what storms there are, in some sense, are becoming more intense. And we, again, I haven't had time to go into the science of this, but we understand that part of it fairly well. But we can't use historical databases to estimate hurricane risks very well because they're too flawed and too short. So we actually bring physics into the problem. And those models, which are encoding our understanding of physics, have gotten steadily better. I'm showing you here for a snapshot from a global weather prediction model. This is an actual satellite image. This is a model, a global prediction model, valid at the same time. You can see, if you squint, you can see differences, but they're pretty similar. This is a model, this is reality. And if you look at the skill of numerical weather forecasts, going back to about 1980 or so, this is 3 days, 5 days, 7 days, and 10 days. They've all, 10-day forecasts, that is, they've all improved, okay? Obviously, the shorter range forecasts are better. The thin curve is for the southern hemisphere, where we have far fewer observations, and the thick curve is for the northern hemisphere, and the difference is shaded here. But the bottom line is that a 7-day forecast today is roughly as accurate as a 3-day forecast was in 1980. So this has been a great success story. We're getting better and better at models. But we're not there yet. Models really don't do a very good job simulating hurricanes. And I don't want to get into a long song and dance about this, but the bottom line is they just don't have fine enough spatial resolution to capture the physics of hurricanes. They try, but they don't. I'm going to skip over this graph for the sake of time. But at MIT, we've learned how to get around that by embedding in climate models, very tiny but extremely detailed hurricane models that were developed originally to help forecast real hurricanes. And we've gotten pretty good at that. And we can generate 100,000 tracks. Here is a picture of the tracks of 50 of the top 50 of 5,000 synthetic events that happen to affect Boston. All right, so this is 50 of 5,000 Boston hurricanes, if you will. We can generate almost as many as we like. These points show where the storms formed, and the colors are an indication of how strong the winds are. And these are all strong ones because we picked the top 50. So we can do lots of statistics on these like this. This is the frequency of hurricanes in hurricane wind speeds within a certain distance of Boston. Here's the wind speed, here's the frequency. This is for the climate of the late 20th century. The red is for the climate of the late part of this century, and the shading indicates the uncertainty in the estimates. Okay. And how do you read this graph? Well, for example, you would expect on average in the climate of the late 20th century, a 64-mile-an-hour wind every 18 years, somewhere within a few hundred miles of Boston, not in Boston itself, within 100 miles, I should say. And then by the end of the century, if we don't do anything, it'll be every 6 years. Likewise, 100-mile-per-hour wind, you'd have to wait forever to see that within 100 miles of Boston from a hurricane. But by the end of the century, you only have to wait 114 years. It's still rare, but a lot more common than they used to be. Same thing we can do for storm surge for water, which is one of the most dangerous aspects of hurricanes. Same kind of graph. This is frequency, but now on this axis is the height of the storm surge. A storm surge is like a tsunami, but it's made by wind rather than an earthquake. And so the future also has built into it an assumed 1 meter sea level rise, which is sort of a central estimate. And so 2 meter storm surge, which would flood downtown Boston pretty easily. Basically never at the end of the 20th century. You have to wait 1,600 years. By the end of the century, only 20 years. That's a lot of change. So is this our future? Will it look like this? Back Bay, Boston, the Charles River. That's my building at MIT. It's still there, but can you get to it? Nope. Now that I've painted some doom and gloom, I want to make this bold pronouncement. That is, where there's risk, there's opportunity. And I don't mean that cynically. I mean, there's an opportunity to improve the world, maybe catalyzed by the fact that we have to deal with risk. And let's talk about this in numbers, okay? So the current global annual energy market's about $8 trillion. It's a huge market. It's going to grow fast because of hope for diminishing of poverty in the third world. We hope that they develop, at least I do. Most people I talk to don't wish them to remain in poverty. And that's going to increase a lot the demand for energy. And energy is much too slowly being decarbonized. There are a lot of people who would like to see it decarbonized. There's a market for it. And so it follows, and this is not rocket science, obviously, that nations and industries that innovate clean energy will become market leaders. So this is a huge opportunity from that standpoint. And this would be a good time for countries like the United States not to just sit back and wait for this to happen, but to catalyze energy innovation. What are we shooting for here? So what are the solutions and opportunities? Well, they're renewables like solar and wind. Solar and wind receive a lot of attention, deservedly. The prices of photovoltaics and wind turbine are falling very rapidly. And if you're as long as you are low market penetration, less than about 30%, which we certainly are in most places, we can deal with the intermittency of these sources through baseload, which alas, today is mostly coal and natural gas, a little bit of nuclear in there. And you have to maintain the full capacity for those times when the sun isn't shining and the wind isn't blowing. If you want to go to high market penetration, you have to rely on storage. You have to store energy between when you're making it and when you're using it. The best current and near-term projected method is lithium-ion batteries. Maybe that will change. Right now, it's the best one. For 12-hour storage capacity, you're talking about $4,000 per kilowatt hour, and that's projected for 2025. By 2040, we're going to need 5 trillion watts of capacity globally. And to store that for 12 hours will cost about $1 trillion a year for 20 years. So we're talking about $20 trillion. Unfortunately, the lifetime of these batteries is only about 10 years. So you need to replace them. You're talking about $2 trillion a year at that point. So solar and wind are great up to a certain point. If you try to push them beyond 30 or 40%, you either have to use your neighbor's power generation. Germany, for example, which got up to 40%, relies heavily on Switzerland, France, and so forth for when it's not generating. If you really want to do that on a large grid scale, you got to start storing it. And all these numbers are only getting you 12 hours of storage. So there's that limitation. Nuclear has a bad name, but I'm going to show you that that's probably undeserved. Projected electricity demand equivalent to the output of about 2,500 2-gigawatt reactors. You'd have to build about 125 of these per year to meet this. And that's assuming you're going to replace all the electricity. Of course, you wouldn't. The current cost to build one of these reactors in places like South Korea, who does it well, about $4 billion. That amounts to about $500 billion per year, which is about 0.6% of current world domestic product. But when you're finished building them, the good news is that their service life is 80 years, roughly speaking. And we've already done it at that rate in, for example, France and Sweden in the 70s and 80s. Sweden built one 4-gigawatt reactor per 10 million people per year. If you scale that rate up to the world population, it's actually a lot more than you need. All I'm saying here is we've done it before, right? So it's at least possible to do it. But there are problems with those reactors. And that's old technology. We can do much better today. There are all kinds of designs. I don't have time to talk about them all. There's molten salt reactors, which are passively safe. Some designs can help process all the waste that's been accumulating from the old generation of light water reactors. They operate not at super pressure, but at ambient pressure. They can run on thorium, which is not as well suitable for weapons. And again, they have a long plant lifetime. Now, people think nuclear power is dangerous. It's just plain wrong. Okay, this is deaths per trillion kilowatt hours by source around the world. Coal is king, kills huge numbers of people. Oil, gas, hydro, solar, nuclear is at the bottom. And the nuclear that's in the United States today, well, 13,000 premature deaths annually in the US from coal production and combustion, 8.7 million globally, which means that more people, this is perhaps the most important thing I'm going to say to you at this part of the talk, more people die every 3 days from fossil fuel particulates, that is things that cause lung diseases, that have died in the whole history of nuclear power. But there are plenty of people who would like to shut down nuclear power and replace it with fossil fuels. And that's happened in some parts of the world. Now, going back to just the plain old problem of eliminating fossil fuels, what I'd like to emphasize to you is there huge benefit, no matter how you do it, there are huge benefits from eliminating fossil fuels. The World Health Organization, 4.2 million premature deaths from particulate pollution. That's actually been upped a lot. Global economic value of life, $100,000 is what the economists tell us. I don't know where that number comes from. But that means, if you believe it, that by 2040, we'd be saving $400 billion per year in the economic value of lives saved by not burning fossil fuels. It brings net costs, for example, nuclear from $500 to $100 billion per year, if you include those savings, and you apply the same number to other sources of generation. So cheap green energy would permit large increases in per capita wealth in the developing world, something we hope for. And energy conservation would yield a net benefit even before climate change is considered. Not conservation, conversion. So there's a good reason to do this even if we didn't have climate change to worry about. So the climate costs of continued dependence on fossil fuels, on the other hand, could be very large. It's estimated to be on the order of $3 trillion per year by later in the century. So let me wrap up so that we have time for discussion. We're altering the composition of the atmosphere at considerable risk to ourselves and to future generations. There's no doubt about that. The levels of risk one can argue about, but the fact that it's tangible risk is not really debatable today. The long-term risk is dominated by extreme events. They're the things that get you in the long run and the things that cost a lot. We're still stuck trying to estimate risk of extreme events with historical records, which just aren't up to the task, even if the climate were not changing. So I am advocating, have to my scientific colleagues, that we embrace advanced modeling techniques because they've gotten so much better for assessing climate risks, not just global climate change. Quantitative assessments of risk to the economy, and I didn't actually give you the data by which you could draw this conclusion. I'm happy to talk about it if you like, would warrant spending at least 2% of world domestic product on mitigation. And we're not spending anything like that. So the really conservative economists say that climate change is going to cost 2% of world domestic product before very long. And the same economists will tell you that you should spend at least as much as the risk is likely to cost to avoid that risk. We do that every time we buy an ordinary insurance policy. We end up paying more to mitigate the risks than the risk is likely to cost on average. Finally, if we are smart, and I didn't really give you the argument behind this, but right now smart means an optimal combination of nuclear power and renewables, maybe 40-60. We can do that pretty quickly if we want to. And we can do that at about 0.5% of world domestic product. And if we wanted to do not just electricity, but all energy, it's also around 2% of world domestic product. So what are we waiting for? I'll leave it at that and happy to entertain your questions.
Well, thank you so much, Dr. Manuel, for speaking tonight. And I think we're going to move on to some questions now from the audience. So I'm going to be alternating between in-person questions and then questions on Zoom. So if you have an in-person question, if you could move to the microphone on my right. And on Zoom, you can raise your virtual hand and you can unmute yourself when it's your turn. So we would appreciate it if you could introduce yourself and keep the questions brief. So would we like to start a line over here?
Hi, my name's Maxime Ernst. I was wondering how much emphasis should we be putting on individual action versus corporate versus government action?
Well, that's a really good question. Thank you for asking it. And I think the scale of the problem really demands collective action. And I'd be the first one to love to tell you that we can just do it by things we do as individuals, changing light bulbs. And I'm greatly in favor of that, by the way. I changed all my light bulbs, quite literally. But it's not going to solve the problem. And the reason that's not going to solve the problem is the huge ongoing and hoped for growth in the economies of very underdeveloped nations. So we need to agitate for collective action to catalyze a much more rapid transition away from carbon-based energy and I didn't talk about this in my talk, the means of taking carbon out of the atmosphere and burying it. That's another thing you can do, but it's going to take a lot of collective action of getting together, pressuring politicians, whatever it takes.
Thank you.
Sure.
All right, we're going to go to Zoom for our next question. Janet, do you want to unmute yourself?
Yes, I'm curious if you would want to comment on fusion.
Oh, yes, it's one of my favorite subjects because I know a lot of the people at MIT involved in it. For the first time since I've been an adult, there's good reason to be optimistic that we're going to get fusion power maybe as soon as 15 years. Now, some people have been saying that for a long time, but there's been a big technical breakthrough, which has to do with superconducting magnetic materials that have allowed that. And as you probably know, in your backyard there at the old Fort Devens, MIT is building the first, what will likely be the first energy generating fusion reactor. Now, if we can get to fusion, has very few of the problems of nuclear fission, and it basically would solve the world's energy problems if we can do that well and economically.
Thank you.
Do we have an in-person question to go next?
Yeah. Hello, Professor Emanuel. Thanks for giving the talk. I'm Brad Hubbard Nelson. I'm curious on the risks of sea level rise. What is the thinking in terms of just gradual sea level rise versus breaking up the ice sheets and some sort of rapid sea level rise over a period of a few years? Is that something that people can calculate now? Well,
You put your finger on what keeps people like me awake in the middle of the night, quite literally. That is part of understanding a system better is becoming better acquainted with your ignorance of the system. I think I call that wisdom. Sorry about the 8 bells that are going off. What we have come to understand is that from looking at geological records and other things, that the great ice sheets on land, as exist today in Greenland and Antarctica, are capable of sort of an instability where the individual glaciers on the ocean suddenly speed up. We're not very confident in that, but we're pretty confident that we're ignorant of that. And we've seen evidence that that's happened in the past. And if it happened on a massive scale, you could get a rapid rise in sea level. Since we don't understand the problem, we don't want to stick our necks out, say, and ring a lot of alarm bells. But we have to be honest to say that it's within the realm of possibility. But unfortunately, right at the moment, we can't say much more than that.
All right, I think we have an on Zoom question. I cannot see where your hand is raised on here, but I can see it on the screen. Pamela, would you like to unmute yourself?
Thank you, Pamela Dritt, for your wonderful lecture. What do you think of using liquid air as batteries, liquefied air, with the same technology that we use for liquefying natural gas and liquid nitrogen? We can, as a byproduct of liquefying the air using solar and or wind power, remove the carbon dioxide and the water vapor and get drinking water and cheap ways of removing the carbon dioxide and other impurities to use to bury to get it out of the air, at the same time as we're using that as a kind of a giant heat pump to store the solar and wind energy to equalize the grid.
Mhm.
Also, massive heat sand pit batteries and the other currently in existence battery technology.
Well, I have to profess some ignorance about air batteries. All I can tell you for sure are two things. There's a lot of research going on in a lot of different places on batteries or energy storage full stop. It doesn't have to be a battery, of course. If you can solve the storage problem, you really have it made, okay? The other thing I can tell you is that right now, nobody's demonstrated a storage technology that makes much economic sense at very large scale. There are claims here and there. I couldn't address each one of those, but the energy experts I do talk to, energy, we're not there yet. But there's reason for optimism. I've heard, there are one kind of thing that is being used as iron batteries. That's a real thing that is being experimented with as for long-term storage on the grid scale. So one of the things we absolutely have to do is to put a lot more funds and effort into the whole spectrum of things that affect energy, including storage. But there's a lot of excitement, a lot of research, a lot of startups going on. So I'm pretty optimistic. But if we don't have something in hand, you can't, it's too soon to pick a winning horse, I would say.
Hi, Dr. Emanuel. I wanted you to address the question. You mentioned that physics modeling was being done at MIT and produced good models compared to the more traditional type models. How difficult do you find it, or how prevalent do you find the use of these new physics-based modeling techniques, and what are some of the barriers to getting that to be used more widely?
That's a really interesting and good question, and I'll try to answer it briefly. The short answer is that outside the US, these kinds of models are being adapted fairly rapidly. Inside the United States, not so much, and it's for very complicated reasons that have to do with two things: the way we regulate private insurance and the provision of a lot of insurance by the federal government. The private insurance problem is that when these models suggest in a particular place, as they are bound to, that the risk is higher than somebody thought it was, the insurance companies want to raise the rates. Even if the regulator will let them do that, there's a big hue and cry from the people in harm's way, and they usually succeed in manipulating the political system to lower the risks. And this is a very complicated problem. The other thing is that the rating agencies have relied on the old-fashioned historical method of estimating risk, and they are likely to lower your rating if you stray from those estimates. So there's a whole bunch of complicated and unwise policies in place in the United States that unwittingly have, nobody's out there in a conspiracy, but unwittingly have the effect of locking in the current way of estimating risk. But in other countries, there's more flexibility.
Sounds like a predicament.
There's books written about it. If you're interested, write me. I can send you some, direct you towards some pretty good books on that subject.
All right, we're going to go to Zoom for our next question. So Can McDonald, if you wanted to unmute yourself and ask your question.
Hi, good evening, and thank you. Actually, I'm using my wife's computer. So the photo that you see is, sorry, Canday. The question that I had was, I'm curious how the models, more of a policy question, reconcile, the fact that the first world countries have gained dominance due to, basically on the back of fossil fuels. And yet, in order to achieve these decreases in carbon dioxide and greenhouse gas emissions, we're going to be asking other countries that will be hoping to get to that point through cheaper, use of fuel, which is probably going to be coal or natural gas, how do we help nudge those countries to, toward our way or the global way of thinking, more globally rather than just, hey, we want to increase our global standing in the world as well? Thank you.
Oh, that's a really excellent question. And it challenges a lot of economists and others who have looked at this. I think the bottom line is that we're not going to get developing countries to curtail their development by proselytizing at them, certainly. The best possible thing we can do is to develop and give them or sell them sources of energy or ways of dealing with the carbon emitted by fossil fuels that make sense for them. And by sense, I include economic sense. It's a tragedy, if they all had to convert their energy systems to whatever is available now, it would just cost them too much, cost us too much. That's why we haven't done it very much either. No, really, we haven't made that much of a dent in the carbon emissions and carbon, some emissions in the US from switching from coal to gas mostly. But the other side of the tragedy of the developing world is they are disproportionately affected by the kinds of climate disasters I talked about. A single hurricane killed 500,000 people in what was then East Pakistan in 1970 and is now Bangladesh. They really get walloped by these things. So they get it from both sides. The best thing we could do is develop something that allows them inexpensively and effectively to change the way they use energy and generate energy.
Would you see that as being nuclear? I'm just curious.
Well, as I said in the answer to someone else who spoke up, it's probably too soon to pick a winner, but it's not going to be one winner. Almost certainly it's going to be a mixture of sources. And that mixture will vary a lot from one place to the next. Like, for example, to take an extreme case, Iceland is already completely fossil free because they have plentiful geothermal energy. Norway all runs on hydro, although they drill a lot of oil and sell it to us. But globally, if we had to do it right now, it's going to be a mixture of nuclear and renewables, not one or the other, but both. They work together in a symbiosis that's very good. But as time goes on and technology develops, that mix or the particular mix could change a lot.
Thank you very much.
Sure.
Hi, Professor Emanuel. This is Tara Pisani-Guro. Thank you so much for a great talk tonight. You showed a graph that will stay with me tonight and for many days, but that shows the persistence of greenhouse gases, carbon dioxide in particular, but also methane, nitrous oxide, long into the future. And so even if we were to stop our emissions tomorrow, we are already locked into global warming for centuries. Could you speak a little bit about where you see potential in drawing down our carbon dioxide emissions in the atmosphere? And also, how do we adapt to this warmer, more risky environment that we are inheriting, our children are inheriting? Thank you.
Yeah, it's another wonderful question. Thank you for asking it. There's a lot of work going on in carbon capture and sequestration, including at MIT, but there are many, many places. We actually can do it. And technically, we can do it now. We have the means of taking carbon dioxide out of the atmosphere, just way too expensive at the moment to make it practical. And the question is, how much can you beat down the cost of that? There are a lot of interesting ideas. There's some basic sort of thermodynamic limits on, how energy intensive that process is. But it's really worth working on. And that's why, amongst the many, many things that climate scientists and economists recommend that governments do is to promote this whole slew of research into alternative energy, into electrifying things that now depend on high heat from coal and gas, things like steel production, and just what you said, taking carbon out of the atmosphere. That could reverse, not everything, but a lot of the decline. Otherwise, it's a question of adaptation. And you're right. We're going to right now, even if we stop tomorrow, we're going to have to do at least a little bit of adaptation to the climate change that's already built in.
Thank you.
I hope you don't have too many nightmares over that graph.
All right, we're going to go to Zoom for our next question. So William Kim.
All right, so thank you for the great lecture. And I'd like to ask, is the world currently on track to replace fossil fuels with nuclear fission or other renewables? And if not, I'd like to know what factors are sort of preventing nuclear energy from being more prevalent. And does it have to do with the technical aspect of nuclear plants? Is it not efficient enough, or is construction cost too high? Or does it have more to do with the political sphere?
Well, that's another good question. And I've spent a lot of time on that. I'm going to have a hard time giving a short answer, but I'll try. We have lots of problems with nuclear fission. One is that the existing kind of fission plant, we have a pressurized light water reactor, was never, not even in the 1950s when they started being built, was never considered by scientists to be the optimal design. But it was good for producing plutonium when the military wanted us to be making material for bombs as a side product of electricity and other things. They were also the ideal reactor for submarines, and we developed, those are the first nuclear reactors were submarines. That was the right design for submarines. It was sort of easy to scale it up to, it was a fast thing to scale it up to power plants. It was never the right design. But nevertheless, they were built out like crazy in the 60s and into the mid 70s. And then two things happened. Well, several things happened around the world. We had a partial meltdown at 3 Mile Island, which actually didn't really cause any danger, but it was very alarming to a lot of people. But more importantly than that, we had a lull in the demand for energy around that time. And so the demand, even if it hadn't been for that accident, the demand for nuclear power was, for all power, was sort of not maybe declining, but not going up. And the problem with nuclear is it's a very labor intensive and intelligence intensive enterprise. And we stopped, there was nothing for a graduate in nuclear engineering to do back in that era. So the supply line of talent dried up. And then when we stopped building the plants, the supply line for parts dried up. You can't just push a button and restart that. And then after Chernobyl in Russia and so forth, the demands for safety went way up to very, very high levels. And it's made it, all of those things have combined to make them very expensive right now in the United States. But they're not expensive necessarily in other places. South Korea, which is using an American design, they build them pretty cheaply when compared to, especially if you prorate them over the lifetime of the plant, they're really cheap compared to almost everything else. So it's a long story, and I'm sorry to have given you an incomplete answer, but I could send you some material on that if you like.
All right, David Clark. David, if you'd like to unmute yourself.
Yeah. I was interested in the Milankovitch's theories of precession, not theories, but studies of precession and things on the effect on global change and in the temperature. But that, I assume, has been going on for millions and billions of years. But as I understand it, these glacial periods are fairly rare in geological history. Why are they so rare if this precession and orbit change is so regular?
Yeah, that's so what's going on there is that there's more than one effect on the climate. The orbital changes have always been there. Okay, they're nothing new, and yet they only produce these ice age cycles for the last 3 million years, which isn't that long compared to our 4 billion year history. And we're not quite sure exactly why that's true. One thing that's happened is that since its peak in maybe the Eocene period, say 50 million years ago, the carbon dioxide content in the atmosphere on a 50 million year timescale has been slowly dropping. And eventually it got low enough that these orbital cycles could start to build ice caps. And that's when these glaciations started. So that's a likely answer to your question, but when you go that far back in geologic time, you can't be certain that's the reason, because our measurements of carbon dioxide in the atmosphere that are really good only go back about 1 million years. Before that, you have to rely on much less accurate proxies. But as far as we've been able to tell, it's slowly declining CO2 on the 50 million year time scale that brought this about.
Thank you.
Sure.
We can go in person for our next question.
Hi, Dr. Emanuel. I'm Eliza Potter. My question is, climate change has become such a partisan issue in our country. And I was wondering how you think we should approach that, whether it should be to fight to make it more bipartisan or to find other ways to tackle the issue.
Well, Eliza, that's something that's dear to my heart. I've spent the last 20 years going to very politically conservative groups and trying to get them on board with this climate change, tea parties and so forth. I could tell you some fantastic stories about my experience trying to do that, but I won't. I'll tell you what I've hit on as the most effective strategy for me anyway, and maybe it would be for others. And that is instead of using the stick a lot, by which I mean painting scary pictures of the future. And there's no doubt that we are taking risks. I don't mean to downplay that, but to emphasize the opportunity aspect of that. I've literally had people come up to me after talks at some of these places and say, Emanuel, I don't really buy this climate nonsense, but I'm completely on board with the solution. I've had people say that to me. And they say, yeah, I mean, 8.7 million people per year from particulate pollution from fossil fuel. Yeah, let's do something about that. So they can get very excited if you paint for them an optimistic picture of what the world will look like. See, they're all afraid. Everyone's afraid you're going to take away their Humvees or whatever it is. They don't want that. They're afraid of that. But if you paint it as an opportunity, which it really is, to have a better life, less lung disease, for example, they can get very excited about that. So my advice to you is look at the upside of the transition away from fossil fuels and paint that for them.
Thank you.
Yep.
All right, we'll go to Sharon on Zoom.
Hello, Dr. Emanuel. This is Sharon Jones. I was reading recently, I've seen various things, the Arctic and Antarctic are warming twice as fast, 3 times as fast, 4 times as fast. Recently, there was an article that in March, there was a heat wave in both the Arctic and Antarctic where the temperature was 70 degrees above normal for 3 days. If we experience temperatures 70 degrees above normal, we'd all die. So as you mentioned, we may not really care if the average just goes up 3 degrees or 5 degrees C, so it's a little warmer, but these perturbations could be really catastrophic. And what's your current understanding, or could you share with us a little bit of your understanding and expectation about those kinds of perturbations?
Yeah, so we, in the profession, you're absolutely right. In the profession, we call that polar amplification. It was long ago predicted. It's sort of most of it is fairly elementary physics. And I can't give you a very short answer on that, but when you go to very cold climates, there's not much water vapor in the air. And it turns out that if you take water vapor is actually the most important greenhouse gas, but it responds mostly to temperature. There's nothing we can do about water vapor, really. For a given increment in temperature, you get much more bang for the buck from radiation from water vapor if you start at low temperature. So, a degree of warming at the pole produces much more greenhouse effect from water vapor than a degree of warming at the equator. So that's one piece of the physics. The other is melting ice, especially sea ice. Sea ice doesn't contribute to sea level rise, but ice is white. It reflects sunlight. If you melt it, you got dark ocean water and it's suddenly absorbing sunlight. That's another feedback. And there are a bunch more, and they all serve to amplify what's going on at the poles. But that's important because that's where the big ice sheets are. So even though most of us don't live, very few people live anywhere near there, it's a big concern.
We have time for one more question. So if Zeno, I'm so sorry if I'm mispronouncing your name. Do you want to unmute yourself and ask your question?
Hi, Dr. Emmanuel. I'm Mansour Zenuzi. First, thank you for the great talk. I agree that for reducing the slope of increase of CO2, at least for the short term, the nuclear energy has to be part of the portfolio of the energy that we use. But as you know, we're gonna run out of the nuclear fuel, uranium and other things pretty fast. And so we have to come up with the other, different solutions. Have you heard about the salinity gradient energy? Well, the Gibbs free energy thermodynamically, mixing the river water with the ocean. We have a mixing process. We destroy a lot of energy. Like it is a reverse, basically, for people that don't know, is just the reverse of the desalination. We spend a lot of energy to desalinate water. When all the river end up to the ocean, we can capture some of that. One of your colleagues in the mechanical department is working on that. But I think we have to spend more money and energy on that. And as you know, Statkraft, the Scandinavian basically company, hydro company, made the prototype, but again, disbanded because of the problem with the membrane, and the economically wasn't feasible. And it's a public company that has to answer to the investor, so they didn't want to keep losing money. But that should be part of the portfolio again of the solution. And then, it's just curiosity if you know anything about that and if you're familiar with any work done in that area. Another thing is, can you or somebody who organized this make your presentation available for educational purpose or your slide?
And that's up to the organizers. I'm happy to do it. But to answer your question, just a couple of things. Uranium supply is not that great, you're right, but a lot of people are switching to thorium, which is much more plentiful. And in fact, I think amongst nuclear engineers, the supply of fuel is not a concern. Amongst all the concerns they have, that's not one. But I think, I don't know very much about your main point about that branch of research. There is, for example, thermal potential between the deeper ocean and the surface ocean. It's warm at the surface, it's cold at depth. You can use the energy in that temperature gradient. But the broader statement is that let 1,000 lights go on here. We need to be putting more funding into even exotic ideas for how you might generate energy. And including certainly more funds into the ones we already know about, solar and wind. They could be made more efficient, for example. So too soon to pick which the winners are going to be. So we really ought to be putting more funding into a lot of those ideas. But
untapped renewable energy.
Yeah, yes.
Well, thank you all for your thought-provoking questions. And once again, thank you to Dr. Emmanuel for presenting to us tonight. I'm going to pass it off to Janet for some closing remarks.
Well, I also want to thank you, Dr. Emmanuel, for a fascinating and inspiring presentation. We really appreciate having you with us tonight, taking time out of your busy schedule. And thank you everyone for joining us tonight, both in the live audience and on Zoom. And I also want to say this is being recorded and it will be available on the
I could hear the fiber completion people.
Oh, they froze.
Yeah.
What do you think of carbon dividend?
Oh, you'd have to ask an economist about that.
Oh,
Yeah.
you don't need an economist. It would.
I've lost you.
No, they muted me. They came back, I think. Are they back? Maybe not.
I'm talking, okay?
Okay, we lost you for a
Closing
moment.
remarks, okay? On Saturday, there's going to be a Cooler Concord Climate Festival, which will be held on the lawn next to the main library from 10 a.m. to 2 p.m. The festival will feature art, food, information, and activities for children, youth, and adults, and will be co-hosted by the Concord Carlisle High School Green Team, Mothers Out Front, and many others. And you may see some superheroes there. These sustainability events will be followed in the coming weeks by ones on heat pumps for heating and cooling your home, a workshop on energy savings, and an electric vehicle event. Those of you who are here, please take the opportunity to learn more about these events from people at the tables outside the hall, and of course, the information on the Cooler Concord website, which you can find outside too. Okay. Thank you, everybody, for coming.